Last time, we ended on something that sounded impossible. Two strangers who have never met, with no trusted courier, talking only over a wire that somebody is listening to completely, need to end up holding the same secret that the listener does not have. For 2,000 years, that was accepted as simply not possible. Then, in 1976, it was published, and the solution is so simple that you can do it with paint. By the end of this video, you will be able to explain it to anybody. Two figures at opposite ends of a wire, a listening figure perched on the wire between them, labeled Alice, Eve, and Bob. Let us give them names because cryptographers always do. Alice on one side, Bob on the other, and Eve in the middle, who hears every single thing they send. Not some of it, all of it. And to make the point properly, we're going to do this with buckets of paint, out in the open where Eve is standing right next to us watching. Step 1. Alice and Bob agree on a starting color, out loud. Let us say yellow. They do not hide this, they announce it. Eve writes it down. Yellow. Everybody has yellow, and that is completely fine. A bucket of yellow paint in the open with Alice, Bob, and Eve all looking at it, labeled public. Everyone knows. Step 2, and this is the only private moment in the whole process. Alice picks a secret color, red. She tells nobody, she never sends it, it stays in her house. Bob picks his own secret color, blue. Same deal, he tells nobody. Eve has no idea what either of them chose. Alice holding a bucket of red behind her back, and Bob holding a bucket of blue behind his, each labeled secret, never sent. Step 3. Alice takes the public yellow and mixes in her secret red. She gets orange. And now she does something that feels reckless. She sends the orange across the wire, right past Eve. Bob does the same. He mixes the public yellow with his secret blue, gets green, and sends the green across. Alice mixing yellow and red into orange and sending it along the wire. Bob mixing yellow and blue into green and sending it back. Eve watching both buckets pass. So take stock of what Eve has now. She has the yellow because it was announced. She has the orange that Alice sent. She has the green that Bob sent. 3 buckets of paint, and she has missed nothing. Eve holding 3 buckets labeled yellow, orange, and green. Captioned, she heard everything. Now, the clever step. Alice takes the green bucket she just received from Bob and mixes in her own secret red one more time. So Alice is now holding yellow plus blue plus red. Meanwhile, Bob takes the orange he received from Alice and mixes in his own secret blue. So Bob is holding yellow plus red plus blue. Look at those two carefully. Yellow, blue, and red. Yellow, red, and blue. That is the same 3 paints. They have both arrived at the identical color, some muddy brown, without ever sending it, and without ever telling each other their secret. So pause the video and ask the important question. Eve watched all of that. She has the yellow, the orange, and the green. Why on earth can she not make the brown too? Here's why, and it is the entire secret of modern cryptography. To make that brown, Eve needs yellow, red, and blue. She has yellow, but she does not have red and she does not have blue. She has orange, which certainly contains red in it somewhere, and green, which contains blue. To get the red out, she would have to take the orange and unmix it. And unmixing paint is impossible, which should feel familiar because that is exactly the one-way street from our first episode. Easy forwards, hopeless backwards. Alice and Bob were only ever asked to mix, which is easy. Eve is the only one who would need to unmix, which is not. That is the whole idea. Mixing is easy. Separating is hopeless, and each person adds their own secret last, so they both end up in the same place by 2 different routes. Real systems do not use paint, obviously. They use enormous numbers, and instead of mixing, they use a particular kind of arithmetic that is quick to do forwards and, as far as anybody knows, hopeless to reverse. But the shape is exactly what you just watched. A public starting value everybody can see, a private value each side keeps, one exchange in the open, and both sides computing the same result. That result becomes the shared key for the fast symmetric encryption we met last episode. This is called a key exchange, and the published version carries the names Diffie and Hellman. There's a lovely footnote here. Researchers inside a British government agency had quietly worked out the same idea a few years earlier, but their work was classified, so the world did not find out until the 1990s. Two sets of people solved a 2,000-year-old problem within a few years of each other, and only one set got to tell anyone. And notice something genuinely strange about what happened. That shared secret was never sent. It never traveled down the wire in any form. It did not exist anywhere in the universe until both sides calculated it separately at the same time in two different places. It's not really a shared secret. It's a jointly invented one. Now there is a second idea in this family, and it is the one most people have half heard of. Instead of both sides mixing, what if you made two keys that belong together as a pair, where one locks and the other unlocks? Picture posting somebody an open padlock while keeping the only key. They can snap that padlock shut on a box and send it back, and they cannot reopen it, and neither can anybody who intercepts it. Only you can, because only you kept the key. So you can hand out open padlocks to the whole world quite safely. An open padlock being posted out to many people while a single key stays home, labeled public key out, private key stays. That is public key cryptography. The padlock you hand out is your public key, and you can publish it anywhere, on your website, in your email signature, on a billboard. The key you keep is your private key, and it never leaves your machine. Anybody can lock a message for you, only you can unlock it. Because the two halves do different jobs, this whole family is called asymmetric, in contrast with the symmetric encryption from last time, where one key did both. So why do we still bother with symmetric encryption at all? Because asymmetric is slow, dramatically slower, which is why almost every secure connection you make does both. It uses the asymmetric trick once, at the very start, purely to agree a key, and then it switches to fast symmetric encryption for the actual conversation. Your browser does exactly that in the fraction of a second before a page appears. A timeline of one connection, a short segment labeled asymmetric, agree a key, followed by a long segment labeled symmetric, send the data. Now the honest part, and it is a serious one. We solved the problem we set out to solve. Alice and Bob can now agree a secret in public, and Eve cannot listen in. But look closely at what we have not solved. Alice knows she is talking to somebody. She has no idea who. Suppose Eve stops merely listening and gets in the way. She does a complete handshake with Alice, pretending to be Bob, and a separate handshake with Bob, pretending to be Alice. Now there are two perfectly secure channels encrypted. Alice is happily encrypting to Eve. Bob is happily encrypting to Eve. Eve reads everything and can change anything. And both of them see a padlock and feel safe. This is called a man-in-the-middle attack. Eve sitting between Alice and Bob with two separate secure lines, reading the messages in the middle, labeled, both feel safe, neither is. So here's the big picture. Two strangers can agree on a secret in the open because mixing is easy and unmixing is not, and because each of them adds their own secret last. Publish one key and keep its partner, and anybody can lock a message that only you can open. Use the slow, clever mathematics once to agree a key, then the fast method for everything after. But encryption on its own only buys you privacy. It does not buy you identity. A locked door is not much comfort if you cannot tell whose room is on the other side. So next time, we work out how to prove who somebody actually is.